Receptive. טוב, אהלן לכולם.
באנגלית, אולי יש פה דוברי אנגלית.
אהלן to everyone. My name is Udi Zohari. I'm going to teach you the visual system in the next 4 meetings. And we shall start immediately. But I need to get some information from you. First, there are 3 people who are giving their lectures with me. You should come by, okay? You should get the papers, read them, and we should sort of go over this because they're not trivial, okay? Don't leave it to the last moment. No fashlot, okay? So please approach me as soon as possible. Now, today we're going to have the session without a break simply because I have to pick up my youngest daughter at 1:30. Okay, maybe 1:33, but so I'll have to rush through this, but it's going to be only today, okay? So don't worry. Third point. I like to have this sort of as an interactive discussion, okay? So there's a lot of stuff, but it's not crucial that we go over all the stuff. It is crucial that first you enjoy this, you learn something new, and that you get exposed to what we're sort of into the field of vision. So please, if I'm unclear, interrupt me, let me know where we stand, okay? Fourth point, who here has sort of a background in studied biology, heard something about the visual system before in sort of heard my course, I give a course on neural mechanisms of animal behavior in which I teach vision. So 1, 2, 3, you? 4. 5. Okay, so there's going to be some parallels, but there's going to be some new stuff. So don't worry about that. The rest are, and how many of you are from LSEC students? Okay, so quite a few. Okay, so I guess we should start, and so I'll be talking about the visual system. And first, just to characterize the problem, okay? And the problem in terms of when you think about vision is that, okay, this is the first question I ask usually students, BSc students, but I'll ask you as well. Okay, what's the problem with vision? Of course, you have a sort of, everyone knows that there's a lens, and you know from your optics in high school, probably in 2nd grade in your high school, you heard that, okay, there's a lens, and therefore there's an inversion of the visual image so that the image is inverted. Okay, so there's a problem to invert it back to its original position. But I claim that this is not the case with vision, that there's a much more basic problem. And it's probably sort of illustrated in this form here. And I'm talking about the fact that, okay, on the retina, all you have is levels of activity, right? I mean, basically you see this image, and there's patches of black and white. Right? And think about them as patches of black and white because you have an array of these photoreceptors which are each is sensitive to light in its specific position in space. And you can look at this as sort of as here the numbers correspond to the level of activation or the light level at each photoreceptor. Okay? These detectors of light detectors. And of course the problem is, when you think about it, is not that the image is inverted, but that you have to somehow read out these changes in levels of light, okay? and interpret them in a meaningful way, right? And this is not done, it's not that, okay, you have an image of the outside world on your retina, and this is translated into electrical activity, but there's no person inside your retina looking at this image on your retina. So the whole thing is to make sense of this level of activation and figure out what is the visual scene. And of course, another amazing thing about it is this is an internally learned procedure. It's not something that you teach. I mean, so here's the case here. I don't know if you recognize what's going on. Quite unusual, right? But, okay, this is the tsunami, okay? And you see people, you know, usually you don't find people up on the electricity lines, right? But here they are because they're trying to sort of avoid the floods, okay? And of course, never mind that, it's a nice image, but it's sort of, the amazing thing is that you see this and you immediately understand what's going on. And you have learned to interpret an image, although first you have never seen that specific image before, okay? And no one has taught you, okay, this is a horse, you see 1,000 horses and then you learn to sort of, that you are taught that this is the horse 1,000 times, and then you learn to sort of generalize to the next million horses that you see in your life. No, you have learned this internally without a sort of a teacher that has to instruct you. So that's something that's amazing. It's true about all the senses, but that's some of the capabilities of our brain to learn this, okay? And of course, in terms of perception, you have to understand the scene, and we think about perception as a sort of a prerequisite for action, right? I mean, the whole thing about perception is not just to perceive the world without acting on it, but to perceive and predict what's going to happen to optimize your actions. And as we shall see, this is just a sort of to tell you where we're going. We're going to talk about vision in terms of different levels of vision, starting from low-level vision, and then going to intermediate-level vision and high-level vision. And of course, the hierarchy is such that, okay, there is some hierarchy in the sense that, okay, vision starts at the retina, and we'll talk about, you know, the pathways from retina to V1. But there's also feedback going back to affect processing in early areas. Now, not to the retina. Okay, so you know about the retina, there's a bottleneck in the sense that there's the optic nerve, and the optic nerve has something like 3 million nerves that go to outside from the retina, reaching the brain, first the LGN, and from there to cortex. And this is a bottleneck so that there's no feedback going from the brain back to the retina, okay? And we'll talk about this as we go. I'm just giving you what includes in low-level vision and then intermediate-level vision, and we'll get back to that. That's just a scheme to think about this. And again, the idea is not to think about this in terms of a sort of a pyramid, that there's just a wave of information from the retina up to cortex, but clearly there's also feedback from cortex, from various areas in cortex back to earlier areas. So we're going to talk about this as we go. Okay. And this is, again, just a scheme before we dwell into the retinal processing in terms of where we're going to head, cortical processing, and gives you some ideas about the fact that, okay, the blue lines are feed-forward lines, say from V1 to V2 or to V3 and so on, and the red lines are feedback connections. So you see that this is a highly connected network, including some subcortical regions that we're going to get into. Okay, so this is going to be something that we're going to touch when we get to the third lecture, and then the students' lecture later. Okay, but today we start with low-level stuff, talking about the retina. Okay, so when we're talking about visual, early visual processing, we're going to talk about the processing at the retina, and then a bit about processing in the LGN, culminating in the primary visual cortex. And I want, okay, and you're going to see that my lecture is somewhat eclectic. We're going to have some computational aspects, we're going to have some physiology, and we're going to have some evolutionary aspects. And I think the first thing to start with is really the evolutionary aspect. Because when you talk about vision, I mean, this is the, I think, key example where people think, well, you're talking about the vision. It's such a complex process. How can you ever think that this has developed by sort of selection and mutation process and natural selection? It seems like completely counterintuitive. Okay, and I think Darwin was aware of this, and he mentioned this, and I think we should start with Darwin. And he said, if numerous gradations from a simple imperfect eye to one complex and perfect can be shown to exist, each grade being useful to its possessor, as is certainly the case, if further the eye ever varies and the variations are to be inherited, as is likewise certainly the case, and if such variation should be useful to any animal under changing conditions of life, then the difficulty of believing that a perfect and a complex eye could be formed by natural selection, though insuperable. Frankly, I don't know what the word means. If anyone knows here, I would be happy to learn from Darwin. By our own imagination, no one knows? Okay. Should not be considered as subversive of the theory. Okay, so but Darwin was aware that vision would be the classical example used by the creationists against the idea of evolution. And I think it's important to, if you've never heard this, it's important to be aware of this. So the first thing is, okay, if you look at the evolution of the eye, it didn't get to the mammalian eye in a day. No, there was quite a process there. So initially all you had basically is just photoreceptors, which basically are sensitive to light, and there's a region of photosynthesis cell so that you can detect light. Okay. And then I won't go to, and then you have this stage of a depressed folded area, and you can find, the interesting thing is that you can find what's called living fossils of these levels in evolution. So the planarian cup in this animal, sorry, I don't remember what the animal is, we'll see in a minute, okay, is a case where you have only a basically depressed folded area which allows limited directional fluidity. So you can tell, okay, if the movement is this direction or that direction. And of course, the image is very unclear, very blurry, but you still get some direction selectivity, so you can tell something about movement. And then you go to the stage of a pinhole, and finally you can sort of add the lens, and so on and so forth, and you get to what is the human eye or the mammalian eye. Okay, and this is also a process in which, okay, I'm giving you here some examples, okay, living examples of these processes. So here you have, for instance, in several animals, most of them are marine animals, okay, like the abalone or the nautilus, something like that. You have these different levels of the eyes, so that you are from the most primitive one, okay. In the squid, it's the most sophisticated one, including the lens already, and a layer of the retina, and so on and so forth. So, and these are, I can't tell you the exact date at which these living fossils are. I can't. I think the nautilus is like 400 million, is a living fossil from 400 million years ago. Okay? So it gives you, first of all, a sort of an appreciation of the fact this is a graded vision as we see it today, is sort of a graded, and some animals who are doing fine with very limited vision, okay, because it's sufficient. The idea is that, okay, if you have no vision, to have some vision is a great advantage, okay? If you can tell if the predator is coming from the left or from the right, just from direction selectivity, and you live in very deep waters, okay, that's great, that's enough, okay? So that's something to understand. This is sort of a really proof proof, of course, but some intuition for Darwin's thought that, okay, it's not that we one day opened our eyes and we got to, mammalian vision as we see it now. And interesting enough, another thing is that there's some principles which are common both to mammalian vision and to very primitive vision. Okay, so I'll just talk about one, which is the limulus. Okay, and the limulus is what's called the horseshoe crab. And why is it so famous? Because there's been work on what's called lateral inhibition, which I'll talk about in a minute, which has been done in the 30s and 40s by Hartline. And it's got a compound eye, so it's a very different structure than the mammalian eye, right? I mean, compound eye is also what you find in insects, okay? And so, without going into the final details of this, you still have, you have, instead of one lens as we have, there's many, many lenses, and there's receptive cells who, again, gather light from a specific point in space, okay? And so you have many lenses, not just one, and each of this receptive cell gets light from that specific lens, okay? So that's why it's called the compound eye. And here you can see the lenses and the structure in a cross section to give you how does the eye of the limulus look like. And here is the array. Okay, so here's the compound eye that we see. Okay, and as we move on, here's the eye of the vertebrate, and for comparison, the eye of the octopus. And I forgot to make a point here because I left one slide out, and that is that, as you'll see in a minute, there's some principles that are common to the limulus eye and the mammalian eye. I'll get to that in a minute. And I'll just have you heard about lateral inhibition? Okay, so some of you have heard about lateral inhibition. So we'll see in a minute that this lateral inhibition is something that we can see also already in the limulus eye. Although, as I said, the limulus is a living fossil from, I think, 380 or 390 million years ago. Okay? So some principles are have evolved in parallel in many species. Okay, and here's just something about, here's something about another example of a mollusk in which the eye is more similar to what we find in the vertebrates. So you have already the lens, and you have here, these are the photoreceptors. Okay, and these are the photoreceptors here are the ones in which light is transduced and passed out through what's called the optic nerve out to the brain. Okay? Here's the structure in the octopus, and the only thing that you can see is that actually in the octopus things are better than in the mammalian eye because the layer of the photoreceptors is outside. So you see these blitot, these points here, which are the photoreceptor array. So light comes from outside, is focused on the lens, and hits the retina. Okay, and here transduction is being done in the layer which is closer to the lens than in the vertebrate eye. Okay, so here you have to pass through a layer of other cells which we will mention until you reach the photoreceptors in which phototransduction is being done. So it seems like that this eye is more effective than this one. Is that clear why? Let me ask questions. Ma? Not just because of the distance, because you have to go to a layer in which there are cells. So there's some light scattering due to the cells that you go through before the light is transduced by the photoreceptors. However, nature has found a way to solve this in the vertebrate. And there's an area called the fovea. And fovea is this area where we have the highest resolution. It's the center 1 degree of the visual field, which is about like, spread your hand out and it's about your thumb size, okay? And in the fovea, if you'll see, here's light and all the sort of cells which consist of the retinal network besides the photoreceptors are removed so light can actually hit the retinal photoreceptors without being scattered by other cells, and that's why this is obviously necessary to have the best resolution, okay? And so this area here is free of all these sort of other levels of cells, which is the case in other areas outside the fovea. And we'll get to that in a minute, okay?
So is there any advantage of this? I mean, you explained what is the...
Why did evolution end up being, with this structure or to that structure? I'm not going to get into this. It's quite complicated. First of all, evolution did get to that structure in another species, okay? There's the issue of the fact that photoreceptors have to be embedded in a structure in which it seems that it's more stable if it's in a sort of structure which is called sort of retinal epithelium, which is deeper there. And I'm not getting into all the details. There's a debate about that, and there are some claims that there's an advantage to that, so that there's sort of a trade-off here. Okay? But visually, there's clearly no advantage to that. Okay? Okay. Now, if we talk about the retina and the photoreceptors, I'm not going to talk at all about the biochemistry of sort of phototransduction. You can, there's some mention of this in the chapters I asked you to read, but I'll just give you sort of a brief sort of outline. And basically, there's two types of photoreceptors, what's called the rods and the cones. And notice that there's only one type of rod, but 3 types of cones. Okay? Now, as I said, here's again the fovea that I mentioned. This is sort of you see that in the fovea we have what's called a cone-only area. Okay? So there's just cones here, no rods, and the cones are the ones which are responsible for color vision. Okay? It's important that there are 3 types of cones, okay? Each sensitive to a different element in the spectra. So I think you've seen this in Adi's lecture before. So here this is the wavelength and this is the relative absorbance. And you see that the 3 different cones have their peak absorbance is at a different wavelength. Well, there's only one type of rod here. And so as I said, the fovea is cone only, and we'll get to the fovea in a minute, but the rods, the advantage of the rods is that they are active at very minimal light conditions, okay? So in the dark, don't know if you've noticed this, but just a few points. First of all, in the dark, you're unable to see color. We see black and white at night when light conditions are such that there's just minimal levels of light, then then basically the cones are inactive because there's insufficient light to activate them, and it's only the rods which are active, and therefore you do not see color, as we'll see in a minute. And you see here, this gives you something about the level of luminance that you need to activate the cones and the rods as a function of time in the dark. So you're all aware of the fact that there's what's called dark adaptation. As we move from high light and move to the dark, then there's some time for the system to adapt, changing its pattern of dynamic range. And if you see here, the rods are active at a much lower, so The lower you are here, it means that lower lighting conditions. So at much lower lighting conditions than the cones, typically 4 or 5 basically log levels, okay? So meaning a factor of 10,000 to 100,000 more sensitive than the cones, okay? Yes?
I don't understand how this graph shows the dark adaptation. The dark adaptation is the period when it's like there is a few seconds that we don't really see it.
Not few seconds, you see, it's minutes, okay?
Yeah.
You're here, and I move you to completely dark, okay? And what you see, the dark adaptation, I just mentioned it in brief, is the fact that you see, okay, you need something like 5 minutes to get to the case where the lower you are, it means that the photoreceptor is active at lower light conditions, meaning it needs fewer quanta to activate, okay? And you see that, okay, dark adaptation gets to its full level only after 20 minutes, okay?
So what happens with dark adaptation is only the adaptation of the rod to the darkness, and then they
You see there's some adaptation of the cones as well, but they are become inactive, you know, if your light level is below this level, there's no activation of the cones, just the rods, okay? So this is, and as we'll see in a minute, the cones are the one responsible for color perception, and therefore you are unable at the light levels beyond threshold point, you are unable to see colors because the cones are inactive. Yes?
In light, do rods work at all? Or?
Yes, they are active. But the major effect is on the cones. And we'll see this in a minute about how they're spread in terms of...
Since they also have a sort of a tuning curve, do they also contribute color information?
No, typically the color information is contributed
only when they're
only by comparisons between the rods. We'll get to that in a minute.
You can interact like a red cone and a rod. You will, like, does the brain have mechanisms to do that? I mean, only by the graph you can see that that comparing the rod with different cone might also give you some information.
Right. But typically, we'll get to that in a minute. In the fovea, where we are best to discriminate colors as well, okay, there are no rods to start with. And the next slide, just to point out, unless it's, okay, go ahead. No.
So in dark, yellow would be darker than green. A yellow slide would be for us much darker blackish if we are 100% with the rod.
Yes, okay, so you're absolutely right that in the dark, all we have is this graph here, okay? So you don't know if you have actually, if you have sort of used monochromatic light at the greenish sort of wavelength, then the chances of absorbance are higher than a yellow, okay? So you would need less light if it's at the green spectra than yellow to see the same structure. But you're not going to interpret this as being greenish or yellowish. Okay, that's the point here. Okay, and one more thing. Okay, so a small digression into color vision, because it's an interesting fact here, and that is, okay, so I mentioned that there are 3 types of cones. Okay, the red, the green, and the blue. And here's the visible spectrum. And here's the problem of color perception. How do we perceive color? You probably know that it's some contribution from what's called the color matching, from the red, from the green, and from the blue receptors, right? So there's, in color, I don't know if you are aware of this, there's what's called metamirrors. I can generate 2 different spectra which will lead to the perception of the same color. Okay, so here's an example, as you well know. I mean, if I take a green light and a red light, okay, source, and just combine them and look at where the area which gets both the green light and the red light, what we perceive is this to be seen as orange, right? And the reason for this is the following. Think about it this way. Here's when you present an orange stimulus, okay? So what is the level of activation that you get in the photoreceptor which is sensitive to the red one? Okay, first of all, it's not sensitive to one wavelength. It has this absorbance spectra, right? So it would get the red arrow here corresponds to the level of activation or the level of activity that you would get from the red cone photoreceptor. And the green here, this here, the smaller level of activity is going to be the level of activity that you're going to get from the green photoreceptor, right? So you can think about it, and the blue, it's outside the blue photoreceptor. So if you're going to use orange, the blue photoreceptor is not going to respond. Everyone's with me here? Okay. And now, consider that you take a sort of a red and a greenish light. Then what I'm generating here is the same vector. Okay, so here's the activation that you get from the red photoreceptor. Is this one, okay? And what about the green? It's this one from the red light, and this, okay. Yeah, well, let's see, did I get this? Yeah, okay. Let's get to the end product, and then I'll try to explain this here. What I want to show you is that if you look at the level of activation that you get from the red and the green for this combination of red and green light, it would be exactly the same as here. Okay, so this and this are the same, and the reason for this is that, okay, if you produce the red light, then you get that level of activation for the red photoreceptor and that for the green one. You produce the green light, you get that level of activation for the green and the same level of activation for the red. And it's smaller because it's the luminance level of the green is smaller than the red. Okay? Okay, but you see that here the level of the red photoreceptor and the green photoreceptor are exactly the same. Right? The absorbance level. Meaning that if you sum up the red effects and the green effects, you get these. Right? There's the green effect summed up and the red effect summed up here. So you get exactly this, and it's exactly equivalent to that. So if all you have in terms of your perception is just how much activation you got for the red photoreceptor and the green photoreceptor and the blue photoreceptor, null here, okay? It would be the same for this type of light and that type of light. Meaning, okay, that you can generate the same, a light percept, which is the same, in this case, orange, irrespective of how did you generate that? Because all you have as output is the level of activation from one photoreceptor, the red photoreceptor, the green photoreceptor, and the blue photoreceptor. And that's the reason why you get metamers, two different spectra of profiles can give rise to the same perception of color. Okay? So that was just to give you something about, okay, some simplistic analysis here done by the visual system, which was actually inferred from psychophysics by Young in 1802. Okay, so he realized the fact that you had metamers, and he predicted that the reason that you see these metamers is because you have these three channels that you use to assess color. Okay, so this is just sort of a point on color. I'm not going to get much back to it, but I wanted you to know something about, the relationship between psychophysics and the representation already at the level of the retina. Yes?
Why isn't those metamers are much more common in our real life? Why, the way I view the surroundings, there's not a lot of times that I see. Okay.
You're unaware of, all you see is the light, green. You're unaware of how did I generate it. I mean, here, I actually show a different example. Here's the spectra, and you see the higher it is, it means there's higher level of energy in a specific spectra. So here's one spectra, and here's another very different spectrum, right? And both lead to the same activity of the blue, green, and red photoreceptor. So there are two metamers. You're unable to tell if this is the spectra or that is the spectra. You're only aware of the percept, which is sort of, in that case, would be a greenish sort of light. Okay? So, okay, that's something about color vision. I'm back to talking about the retina from other aspects. Okay, so when we talk about the retina, and I'll fly through this because this is something that you have in a textbook, but I wanted to give you some sort of principles as we walk through this. Okay, so when you talk about the retina, we talked about the photoreceptors. We mentioned the rods and the cones, and notice here that there's sort of this array, okay, of sort of a small network in which you have information. First of all, okay, so light is absorbed in the photoreceptors and then passed through what's called the bipolar cells to the ganglion cells. And the ganglion cells are the ones which fire action potentials and convey the information out to the optic nerve and from there to the brain. Okay? So that's the basic structure of the retina. And we'll talk about how analysis is done in the retina, but first, something about cones and rods. So here's just, okay, a few things to notice here. So what you see here is, first of all, the distributions of rods in blue and cones as a function of the distance from the fovea. So fovea is your center of gaze, where you're looking at, and what you see is that, as I mentioned, at the very fine 1 degree of center of gaze, there are no rods. Okay, so here's it's only cones, and as you move further away in eccentricity, so if I'm fixating here, eccentricity is the azimuth from 0, which is the center of gaze. You see that okay, the rods, their distribution, the frequency increases and then drops, and the cones are very much dropping exponentially as you move away from the fovea, which is actually quite amazing, because here I am fixating it at the, and I don't have the feeling that I'm unable to perceive color in the periphery, but in terms of my cones, which are responsible for color, this drops dramatically. Okay, so we can assess color also if the proportion of cones to rods is very small, but there's also, notice another aspect here, and that is that there's a hole here. Anyone can tell me why there's a hole? So notice there are no cones and no rods here. Because of the optic nerve, correct. Okay, so the optic nerve is a place in which there are no photoreceptors, because this is the place at which the axils of the ganglion cells are sent out to the cortex, to the LGN, and therefore there are no photoreceptors in that area. Okay, and so just a bit about the physiology. Here's the eye, and I mentioned about the optic nerve going out and reaching the LGN in the thalamus, and then in the analysis, there's some analysis done in the thalamus, and then the information is passed on to the cortex. So we're going to cover this today, and I just want to mention that there's other pathways as well, usually not mentioned very much, which basically bypass this sort of what's called the retinal geniculate. Geniculate is the LGN. Okay, retinal geniculate striate cortex pathway, and these are pathways that go through mainly through the superior colliculus, which is important for orienting your eyes to what's interesting in the world, and also through the pretectum. So major pathway goes through LGN to primary visual cortex, but there's some bypassing pathways that go through the superior colliculus and bypassing the LGN and transmitting information directly to higher cortical areas. And they're important. If you heard something about blind sight before, we think that this is relevant for that. Okay, yes?
It was relevant to my question. I was wanted to ask if we are damaging the optic nerve or the connection between the LGN to the V1.
Wait, one more thing. Optic nerve, if you damage the optic nerve, you're rendered blind completely, right? It's like removing the eyes. So that's trivial, okay?
I'm talking about the connection between the LGN to the V1.
Okay, if you disconnect all the connections from LGN to V1, there's no information through the major pathways. And you're right, okay.
So we cannot perceive vision, but information will come from the folliculi to higher. Yes, you're right. So
first of all, we are rendered blind in terms of our sensation, that we feel that we are completely blind. But there is the phenomenon of blind sight, which is thought to be mediated through information from superior colliculus, for instance, reaching motion processing areas such as MT. We're going to talk about a bit about that later. Okay? So this is very basic, and that is that, okay, most of our visual world is covered by both eyes, right? So there's just the most simple parts, okay, are monocular, but most of it is binocular, allowing for binocular vision, which is useful for depth estimation. And this is done by the fact that, okay, so you look at the sort of, and stimulus is projected here, it's projected both on the left eye and the right eye, and as we said, there's the optic chiasm in which information, so this is from the right visual field, so it reaches the left visual field from both left and right eye, okay? Basic stuff, you probably know that. And I'll just mention very briefly, okay, so people have started doing electrophysiology in the 50s. Classical work is of Kupler from 1953. So have you heard about the on-center receptive fields? Is this something most of you have heard about? Okay, so you're familiar with that. Who hasn't heard about this? Oh, everyone heard about it. Great. Okay, so we can go over this. But let's talk in a few words. How do you get this? Because this is important. So we talk about physiology. Okay, you have a characteristic. And the question is, how do you get the circuitry to get the receptive field characteristics that you see? And so this is very basic, but I'll sort of cover this very quickly. So first of all, the photoreceptor. The photoreceptor, surprisingly, with light, goes through hyperpolarization. Rather than depolarization, hyperpolarization, okay? So actually, it is less active, right? It's hyperpolarized when it sort of absorbs a photon or light. And okay, so light, in this case, leads to decreased glutamate release. So you can think about the photoreceptor, first of all, the network consists of photoreceptors connected to bipolar cells and then to ganglion cells. So this is one the lateral connection between the photoreceptors to the ganglion cells here. And we're trying to understand, okay, as you all know, ganglion cells are divided into two types, what's called on-center ganglion cells and off-center ganglion cells. An on-center ganglion cell would prefer light in the center and light in the center and dark in its surrounding, surrounding angles, right? How do you create this? Well, let's think about first of all about the center. So, okay, there's light, and light now leads. So you can think about this as continuous release of neurotransmitter from the photoreceptor to the bipolar cell. Let's talk about the on-center bipolar cell for a minute. And now, okay, there's hyperpolarization of the cone following phototransduction. And so there's a decreased release of the neurotransmitter, glutamate in this case, okay, to the on-center bipolar cell. So as a result, since the synapse here is inhibitory, okay, between the photoreceptor and the bipolar cell, since the synapse is inhibitory, decrease in the release of the neurotransmitter gets to what? Would do what? You've heard, I assume you've heard something about inhibitor and excitator of the synapses. Okay, first of all, you see the answer, but I just want you to explain. What do we see? That there's depolarization of the bipolar cell. Okay? Why? Because there's less, this synapse is inhibitory. So there's what's called disinhibition in this case. There's less inhibition. Okay? And as a result, there's excitation of the on-center bipolar cell. Okay? And if enough of these on-center bipolar cells are excited, because you can think about many photoreceptors which are connected to these on-center bipolar cells to a ganglion cell. So if enough of them, if there's enough excitation through these on-center bipolar cells, so here the synapse is excitatory. So this is excitatory. So excitation here would lead to excitation here. And if there's enough excitation on the on-center ganglion cells, it fires a spike. Okay? Now this is basic physiology. I hope it's necessary that you sort of know something about this, but if it's something someone is unfamiliar with, I guess all of you should know this. If someone is unfamiliar with this, talk to Adi. He should he should sort of instruct you about this. Okay, so we just sort of follow this here. In parallel, there's the off-center, right? What is the off-center cells? Well, what's characteristic of the off-center cells? They're opposite in their characteristics from the on-center, meaning they prefer dark in the middle and light in the surrounding annulus, right? So what's the story here? You get exactly the opposite response, right? So if you flash light on the center in an off-center cell, you're going to get inhibition, a drop in the firing rate. Why? How do you explain this? So, okay, the photoreceptor is, it transduces light. It leads to decreased glutamate release. This is a question to you. Okay. So here we got excitation. How can we get inhibition on this structure here? Anyone has an idea? Yes, please.
Just depends on the connections.
Correct. Okay. So what's important is, okay, it's true that sort of glutamate is the neurotransmitter here, but what would determine the effect in the postsynaptic side is the postsynaptic receptor in the postsynaptic side. So in the off center, the synapse here is, we talked about here being inhibitory, here it's excitatory. So hyperpolarization of the cone would lead to, since this is excitatory, would lead to hyperpolarization of the bipolar cell. And you have enough of these, you're going to inhibit the ganglion cell. So the off-center ganglion cell, which is, again, a different member than the on-center ganglion cell, actually would be inhibited if there's light in the center. Okay? Great. Now, one other thing to think about is that there's a convergence. So we're talking about, here's this ganglion cell. It's not a one-to-one connection between a photoreceptor, a bipolar cell, and a ganglion cell. In fact, you see here the degree of sort of convergence. So typically there's tens of cones that impinge on a bipolar cell, and there's like 3 to 15 bipolar cells which are sort of converge onto a ganglion cell. Okay? Okay.
Is that how it keeps going on until the visual cortex? So we're saying that
The degree of convergence.
Exactly,
Yeah,
yeah.
so there's basically convergence and divergence as we go on. Okay, we'll see this. I mean, so the principles of convergence are classical throughout the brain. Okay, and okay. There's one thing that I mentioned in the beginning, that there's about 3 million axons coming out from the ganglion cells out to the LGN. Okay, and then when you get to V1, there's actually a divergence because there's about 100 million neurons in V1. Okay, so there's, as I said, convergence and divergence. This is sort of a principle that you can find throughout brain, not just in the visual system. Okay, we should have a break, but we'll continue. So sorry about this. I would need a break, but I'll go on. That's fine. If I'm unclear, please stop me as we go. Okay? Okay. So we talked about one characteristic, and I want to talk about another. So the characteristic we talked about now is the fact that, okay, if you give light at the center, you're going to get a response in the on-center bipolar cell, and you're going to get inhibition in the off-center bipolar cell. Now I'm trying to understand another feature of the characteristic of the receptor field. It's a center-surround characteristic, right? This ganglion cell, the on-center ganglion cell, prefers light in the center, but dark in the periphery. Okay? How does one achieve this? Think about light now impinging on the surround of this cell's receptor field. What would be the outcome? Well, the light is transduced by another photoreceptor who's sensitive to light in a different position in space, right? Okay. And of course, that's universal. Whenever there's light, the transduction leads to a sort of hyperpolarization of that photoreceptor. Okay? And now think about, okay, till now I talked about sort of this sort of vertical connection between photoreceptor, bipolar cell, and ganglion cell. And now I'm talking about the aspect, sort of the horizontal aspect of the system. Let's see it. Oh, that was way back. I didn't realize it was. Okay, so here's your sort of network. So I talked about, you know, photoreceptors, bipolar cells, and ganglion cells. But notice that there are sort of two types of other cells, what's called the horizontal and amacrine cells, and they basically are responsible for the lateral information flow, as written here. Okay, so I want to talk about now, be talking very briefly about these horizontal cells, which connect one photoreceptor to another photoreceptor. Okay, and these photoreceptors are responsible for transducing light at different positions in space. Okay, not immediately nearby, but at some distance away from one another. Okay, sorry about that. So here's the example. Okay, so light is now projected at this at the surround of this retinal ganglion cell. It leads to a phototransduction of this photoreceptor. But notice that there's a connection, as I mentioned before, between one photoreceptor and the other through this horizontal cell. And this horizontal cell has now a sort of an excitatory synapse between this photoreceptor and the horizontal cell. So, inhibition of the photoreceptor leads to inhibition of the horizontal cell. Now, just a few sort of a rule of thumb for you to figure out, okay, as we go, if this should lead to inhibition or this should lead to excitation. Can someone tell me? What's the relationship between this and the nature of the synapse here?
If it's a positive excitation, so it's the same.
If it's excitatory, it maintains the same direction. If it's inhibitory, it reverses. It sort of reverses the direction. Correct. So, here, okay, when you're moving from the horizontal cell has this interaction with another photoreceptor, which is further away. Its receptor field is further away. Okay? So light here activates that photoreceptor, and now we're talking about its interaction with another photoreceptor responsive to light here. Okay? And you see, okay, this horizontal cell has gone through inhibition, and because this is an inhibitory synapse, there's a reversal of the activation. So inhibition here corresponds to excitation of this photoreceptor. Exactly the opposite of what happens with light, right? Usually with light you get inhibition, now you get excitation, okay? And now this photoreceptor is connected through these bipolar cells of the retinal ganglion cell, and again here the synapse inhibitory, so you get this inhibition at the level of the bipolar cell, and to the ganglion cell, this inhibition would translate in a drop of the activation. So, meaning that this cell would not be very responsive to light in the surround, right? So, the best condition to activate the cell would mean a light at the center, as I showed you in the slide before, and dark in the surround, so you don't get this lateral activation, which leads to a drop in the activation. Okay, great. So this is called lateral inhibition. Okay, this principle. Remember I talked about the limulus, and I said, okay, there's some principles which are sort of general and can be seen in evolution, neuronal principles that can already be seen in living fossils from like 400 million years ago. So here's the limulus. This is the work of Kafar Hartline, 1938. He got a Nobel Prize for that. In which he looked at this horseshoe crab, the limulus, and he basically presented light in one position in space, so that he activated this eye compound eye, and another time presented light to activate this compound eye, and then he activated them both. Okay, so when you present light to in one position in space, so that eye is only active, A alone. Here's the spikes. Okay, this is okay. Respective. This is from the 1930s, right? So they had this sheet of paper, and here's the number of spikes that they counted, 53 spikes, and this sort of just the points here are points in time spread, you know, 1.5 seconds between one point and another, so they'll know something about the time frame. Okay. Okay. So you got 53 seconds if you activated A alone through light just for A. If you gave B alone, you got 46 spikes. But if you activate A and B together, you get this lateral inhibition, so A responds less than having A alone, and also B responds less. Why? Because of these lateral inhibitory connections between A and B. Great, right? Just to think that this is sort of a principle that you find in a living fossil. And this is again from Hartline's paper from 1938, showing what I just described to you. Okay, so here in the y-axis, it's the decrease in frequency as a function of fiber A, as a function of activity in fiber B. So there's some threshold, and above some threshold, if fiber B is more active, it generates less activity in A because of this inhibition. Okay? Are you with me? Okay. Only one nodded, so I hope that this is sort of clear. Okay. So this was something about sort of a principle that is sort of not just found in the visual system. You'll see this throughout sensory systems. Lateral inhibition, which is sort of an old principle you can find already in these living fossils. Okay, going back now, I talked about physiology. I want to talk a bit about something about computation. Okay, so the next 15 to 20 minutes are going to be a bit about sort of elements of computation. So I was talking, okay, here's the retinal mosaic that I mentioned. Each of them is a photoreceptor. This sort of photoreceptor array covers visual space. Now, as I said, okay, you present an image, you get an activity of this in this photoreceptor array, and I mentioned something about just now about sort of center surround properties of cells that you find already in the ganglion cells. So remember, photoreceptors are the ones light transduction is being done, but the ganglion cells are the ones which are transmitting the information out to the LGN and from there to cortex. Well, we saw that there's a sort of center surround representation, right? What's it good for? Why do we have this center surround representation? Anyone knows? I don't heard it from the A. Okay, go ahead. Sorry. Yeah. Okay. He's in my lab, so okay. If you didn't hear it directly, you heard it subconsciously. So, okay, go ahead.
From context, it would help us to identify borders and the limits of the
Okay,
picture.
so
Highlight contrast.
highlight contrast. That's the point. Okay, I think that's what you meant as well. Okay, and we'll see exactly how do you achieve a highlight contrast. So in a minute, you've heard about David Marr from Adin, right? Okay, we'll get to David Marr in a minute about this. But let's think again about the sort of the receptor field structure. Okay, so I was talking about retinal ganglion cells. So we're talking about the center surround, and you can think about this in sort of 1D. Of course, the receptor field structure is that way. That the optimal stimulus is light at the center and sort of dark annulus around it. And you're right that, of course, intuitively, the best activation is going to be when you present what? The same stimulus, right? Light at the center and dark in the periphery. And this is a case in which there's strong contrast, right? So this enhances it. This sort of cell is going to be most active when the stimulus fits its receptor field properties, okay? So it's a detector of a change, right? And you're talking about change. What's contrast? A change in luminance between one area and another, okay? So this sort of has intuitive hand-waving explanation. Now I'll sort of mention David Marr in that sense because we can think about this as sort of, first of all, we often think about this receptor field structure as a difference of Gaussian. There's a Gaussian of excitation and a sort of Gaussian of inhibition in the opposite direction, right? And if you sort of sum up this with this being minus here because it's inhibition, right? And notice that this is sort of the inhibition structure is bigger in size than the excitation structure. And if you sum up together, you get this difference of Gaussians, what's called the difference of Gaussian. This is in one dimension, okay? And if you think about this, you know, if you do sort of a cross section across this axis, you're going to get that structure, right? In 2 dimensions, okay, which is actually the actual visual, the receptor field, it looks like that. Okay, but in one in any cross section that you're going to take, it's going to look like sort of a difference of Gaussian. Okay?
Sorry, can I, the difference in size in the last slide,
Yes.
is that present or is peak really representing the whole? Like
It is present. I mean, typically, the excitation, the Gaussian for the excitation is much more narrow than the Gaussian for the inhibition. Okay? And you have this summation of both effects to generate that sort of receptive field structure. Okay? So, did I answer the question? I'm not sure if you.
No, I mean more like the right circle is bigger than the peak for excitation.
The white circle is.
In the last slide.
Oh, that I did just for illustrative purposes. So think, what is the size of this compared to the size of this? That's the question. What is the ratio between them?
The ratio between the peak and it's 1:1.
Yeah, I just did it for illustrative purposes. Typically, first of all, as we will see in a minute, I'm not sure if we'll see, but in our next talk, typically you get the receptive field is not the same everywhere. Okay? The receptive fields can be smaller or bigger. Receptive fields meaning what is the total size of this? Okay? In the fovea, receptive fields are going to be typically much smaller than in the periphery. Okay, so this whole thing changes. Now, in terms of the area of excitation and inhibition, typically, if you sum up the excitation and inhibition, if you give diffuse light, which includes this area and that area, you don't get much activation from the neurons. Why? Because they're balanced. Okay? So diffuse light does not activate the cells very well. Okay.
We always treat the retina as 2D, but isn't it a little curved? Then wouldn't it be more correct to say that it's 3D, just big structure 3D?
What is the third dimension?
Like, it's not only a plane. I mean, it's a little curved in space, isn't it?
Yeah, but the curve in space corresponds to where should you present light so that it will activate the photoreceptor. So you can think about this clearly as a 2D plane.
Surface.
Okay?
Surface. It's a curved surface.
A curved surface, yes, but 2D. Yes, yes. Okay, so I mentioned, that you get the receptive field as sort of what's called a difference of Gaussian, of an area of excitation and an area of inhibition that you get that. Now I want to mention something, what is this? Okay, so that's the structure of the receptive field in 1D, and as we said in 2D it looks like a sort of center circle surrounded by a peripheral annulus. But you can think about this as a second derivative operator. Okay, what is that? Anyone knows? Who knows what's the second derivative operator? Anyone from physics here? Okay, so it's a second derivative operator. I'll mention what is it, okay?
Finally, a word that they can understand.
Yeah, I mean, I have to fit the liking of each of you, right? And 2 minutes for each of you, okay? One from evolution, one from physics, one from physiology. So here's your moment here, okay? And when I talk about a second derivative operator, it relates to David Marr, who wrote his famous book, Vision, which I would suggest you to read. It's from 1982. It was written after he died. He died at the age of 35. And his contribution to neuroscience was amazing in the sense that he set in theoretical approach in many ways, at least in vision, okay, in other fields as well. And he said the following. Well, let's look. I'll jump just ahead. You see this image here, okay? As we say, what's important in this image? Changes, right? Contrast. We talked about differences. I mean, if you look here, this isn't very interesting here, okay? Oh, here, where it's the same. What's important is where are there changes in the luminance, okay? If you had a color picture, then you'd have also changes in color. Well, let's ignore color here, look at the black and white here, okay? So you want something to have the initial representation which is sensitive to changes here. It's like, okay, if you were to send a spaceship to Mars without, not a manned spaceship, Okay, and you want that to have sort of visual capabilities. And let's say, okay, it doesn't have visual capabilities. No, it has Adi here in this room and getting the sort of the image from this rover in Mars, and he has to say, okay, turn left, turn right. Okay, it's not Amun Joshua's rover yet. Okay, so it doesn't have any. It's a stupid sort of machine. But the problem is, okay, that this rover is sort of driving in Mars, and it takes, I don't know, 10 minutes, no, probably seconds. I don't know. Okay, we have to calculate how, you know, depending on the speed of light, how long does it take for light to arrive from Mars to here? It's not instantaneous, okay, for sure, okay. So, and Adis has to drive this rover in Mars, and of course, the longer the battery information is sent, the longer it takes to process this, okay. So you want to, or you don't have the capability of sending many bits of information. So what are you going to do? You're going to try to condense information. How are you going to condense information? You know, when it's all white here, there's no changes here. So what you're going to get, instead of actually giving the level of luminance at each point, what you're going to give is changes in luminance. Okay? Changes in luminance tell you more information than the actual luminance level. Okay? So that's something, that's sort of an analogy to what the visual system does. By being sensitive to contrast, you're sensitive to changes in luminance, not the actual level of luminance. Okay?
So wouldn't that be first derivative, not second? Changes in
Okay, good. Okay, so changes, okay. Changes in the luminance should be first derivative, right? Sorry. Okay, so for the non-physicists here, we're talking about derivative. What are we talking about? Okay, so think about this here. This is sort of x is position in space, and y is your intensity level. Okay, so let's say you move from something. What would that correspond to in the world? Let's see if you understand me.
So it's dark.
I'm not sure that.
Change in luminance.
I'm a bit, you know, I lost my hearing, falling an arm in my right ear, and my left ear is not great.
Down is dark, and
This is dark, yeah.
and the other, this is bright.
Yeah, so you're going to have an edge, okay? And it's sort of, so yeah, right here, okay? That's what you're seeing here, okay? Moving from dark to brighter area, okay? Okay, how can you detect it? If you look at the first derivative, which means changes in the luminance as a function of position in space, you're going to get a peak here, right? That's where, what is the derivative? It's this slope here, right? So the slope here is very high, and then there's no slope here, so this is 0 here. Okay, that's why you're going to get, this is the first derivative now. But you can detect, you want to detect edges. How can you detect edges? You can detect edge as, you know, this maximum here in the first derivative. Or you can look at the second derivative. What is the second derivative? It's this change of slope, right? That's the second derivative here. So what is the, let's follow this. Okay, here the slope is 0, increasing, getting to the maximum, and then becoming smaller, right? And getting back to 0 here. Everyone with me here? Okay? So what would that correspond to? If you look at the second derivative, that's what you see here. Okay, you see what's called a zero crossing. It's positive here, gets to a maximum, and then becomes smaller, okay? And it gets, since the slope is becoming shallower and shallower, it's becoming negative, and then finally again 0, right? So you can detect an edge by finding a zero crossing in the second derivative, okay? That's the analogy. Okay, great. So if you go back, what we have here, what is our sort of ganglion cell responsive to? It's you can think about this as a second derivative operator. What's a second derivative operator? It would look like that, right? Okay, it prefers light at one position and prefers dark in the neighboring positions, right? That's what a second derivative, I mean, you think about this, you want to detect this. How are you going to detect this? You're going to detect this by having exactly the same sort of, the filter you're going to use is the same as your change of light as a function of space, okay? So, interestingly enough, okay, you can think of this as a sort of a second derivative, but it's also modulated by a Gaussian. So you take the second derivative, what I drew here, okay, and you smooth it by a Gaussian, and what you get is what's called sort of what we see the difference of Gaussian. So this is called, in physics, that would be called a Laplacian, and it's sort of the second derivative of the Gaussian. Okay, if you take the Gaussian and you do the second derivative of the Gaussian, you get that sort of shape, which is very similar to the difference of Gaussian. Okay, and so this is the filter that we have here. And the next thing, remember, we have this array of photoreceptors in the retina, right? And you can think about what they do is each of them applies this filter that we just mentioned at a different position in space. So mathematically, that would correspond to a convolution. Okay, what am I talking about? Most of you can't follow the mathematics here, and it's not really important. What's important is to get an intuition here. So the idea is that you have these different filters, right? Each of them has this sort of filtering processing that it's sensitive to, it has something that looks like a difference of Gaussian here, okay? And what I'm saying is that you have these at every position in space. So think about, okay, here's one cell, here's another cell, receptive field, here's a third one. These are receptive fields. It's not the cell bodies, it's the receptive field of these ganglion cells. And this is an array that consists of the whole retina, right? So each of them is sensitive to a different position in space, okay? And each of them has this profile in 1D. You can think about this. And now you have an image, okay? So let's say that the image is something which looks like an edge here, okay? What would be the response of the neurons? So I said, okay, the response of the neurons to this image is a convolution of the receptive field of the neurons with the image. Okay, and I show you here the integral. Let me give you sort of an intuition to that. Let's think of the simple case. Who heard the term convolution before in terms of sort of mathematical approach? Okay. But about half of, okay, so maybe you can help me. Let's think that, okay, take a simpler case. Here's your one function, g of x. Here's another function. So that's your kernel, what's called the convolution kernel. And here's the image. And the image looks like that. That's called this I of x. A convolution of the two, g of x convolved with I of x, okay, is what's written here. But let's understand this in terms intuitively. You take this and you apply it to each position in space. Okay, so this would be, let's say, 0 and 1. Okay, so when this is 0, you don't get any activation. When it's 1, you get activation. So you apply this. What is the convolution here? You see that you sort of apply, you do an integral. So you apply this at different positions in space. Okay, throughout space. So here's x here. You apply this throughout space, and you look at the degree of overlap. Thank you. Overlap between these two. Okay, so if this is 0, okay, what would be the convolution, the result of the convolution in this case that I'm drawing here? 0, right? Nothing. Okay, so that's the gx convolved with ix. Why? Because where it's 1, here it's 0, right? And now you move it by a lag, and you do the same thing. So once they start, there's some overlap between the two. Then the convolution integral will increase. Okay, so here's the function here. So at this point when there is no overlap, the convolution integral is still 0, right? Now we're starting to get some overlap, and it grows. And now it will grow until what point? Until the overlap is maximal, right? So it will grow. I'm sorry. Okay. Let me draw it in the upper part there. Okay, but I hope you understand intuition. Okay, look at the overlap here, and this is okay. So this is Ix convolved with g of x. So as I said, okay, when there's no overlap, it's 0. at some point there starts to be an overlap, so it grows, and it would grow linearly with a degree of overlap between the two. Okay, so it grows linearly, and at some point the overlap is full. So you can't get any further than that, right? And that would be like that, and then at some point as you get here, the overlap is again not complete, right? So it starts dropping. Okay? So this is the intuition for your convolution integral. Okay? So this is what you do. That would be the response of your filtered array, okay? If your filtering properties was like that. But our filtering property looks actually like that, right? So we'll talk about this in a minute. But that's just to give you an idea of what this, without going into the mathematics, give you the intuition of what is this convolution. Now, why do we say that this is a convolution that we have here? Because, as I said, you can think about this. This is, okay, say, the level of luminance in space. And at each point in space, you have a filter responsive to that specific position in space. So in terms of the array, if you look at the response of the population, that would not correspond to the response of a specific ganglion cell. That corresponds to the population of cells on the retina. Which ones are active and which ones aren't. Okay? Now, let's take a more sort of classical example. So here's the image. Okay? Each cell has this difference of Gaussian, or this Laplacian of the Gaussian filtering properties. Okay? And this is the convolution result. Okay? So if you take the filter, this is each cell, and you apply to the image, you apply the convolution, here's the picture you get. So the more bright it is, the more active it is, and the more dark it is, the less active it is. Okay? And what do you see here? Okay, you see that first of all, as one would expect, you accentuate the differences, right? So here, where it's white, there's no change here, okay? But where there's change in terms of position, change of luminance as a function of position, you get this accentuation by this convolution. So this is what the retina performs, okay? Already at the level of the retina, if you were to look at the activity level of the retina, you would see this. Now, let's understand this. This would correspond to the activity of each of the retinal cells, each one responding to a different position in space. Okay, so this is sort of a pattern of activity across neurons in the retina. It's not one cell. That's why you think about this as a convolution. Okay? Now, going back to David Marr. Okay? Well, think about the following. Okay? Here's your image here. Okay? And I do the same thing. So, okay, what I do here is, first of all, convolve the image with your filters. So this is what you get. And mind you, we'll mention this in a minute, but it depends also at the size of your filter. I talked about a center surround filter which looks like that. Well, this is one, but you could have something which looks like that, right? So they're both center surround, but this is sort of a lower frequency than this one, lower spatial frequency than this one. So we'll get back to that in a few minutes. So but let's assume one scale here. Let's say this one here. Okay? So here's the image. Here's the convolution of the image. That's what you see in terms of the levels of activity. Okay? And now what you see is you can see, okay, which one is positive and which one's negative. Okay? So now you're doing sort of a binary decision. Okay, these areas here are below 0, so we will plot them as sort of black, and the ones here are above 0, so plot them as white. Okay, so this is basically a binary division of the areas into ones above and below 0. And what you get here, remember when I talked about a zero crossing? You can think about this. You're generating a zero crossings map. That's great. So here's your original image, and this is a map of the zero crossings, where you had changes, right? Zero crossings are where you're amplifying changes, right? And you see this, okay? So this is sort of the pattern of activity that you're going to get in the retina if you are trying to using sort of this zero crossing computation. Yes.
Why couldn't you get same result straight from A to D by single derivative?
From A to B?
To D.
A to D by
single derivative.
by the first derivative.
Yes.
I think it doesn't tell you which is darker and which is lighter.
D doesn't tell you as well.
Yeah.
If you can go back to the
Okay, wait. Let's go back to this sort of first and second derivative plan. You're saying here, okay.
What's the high, like, you have more information about A when you look at C because then you know which side was higher and which was lower by the direction if it goes first down and then up or first up and then down.
Yeah.
D as well. They will have what
You're right that in principle, I just showed you here. You have the same information in the first derivative as you have in the second derivative. Okay? The second derivative, I guess, and basically, the only issue here, I guess. I don't have an answer I don't have an immediate answer to you. I have to think about this. But I think. But the point is, whatever it is, okay, you want to accentuate edges. Both the first derivative and the second derivative will do the job for you. Okay? The second derivative, you're looking for the zero crossing here. So you may have more sensitivity here. I have to think about this. I have to go back to Bauer and to read what exactly he said about this. But I want you to understand the principle. Okay? And that's not going to change whether it's the first derivative or the second derivative. Okay? And another thing to notice is, okay, you take the original image, and it depends what sort of filter do you apply. If you apply a narrow filter, then you're going to get something which looks like that. If you're going to apply a wider filter, okay, you're going to blur the image, and you're going to get that. Okay, now remember this, it's not an image that you see. This is just a pictorial way of depicting this. What you get is actually levels of activity. This is the levels of activity that you're going to get in the retina if your cells consisted of retinal ganglion cells with a rather big receptive field. And this is if it were a smaller receptive field. Okay? So that's just to point out that. And finally, interestingly enough, in the retina, we have both. Okay? So that's actually quite nice in the sense that we find, okay, so this is exactly the same point as I illustrated before. Here's a small receptive field, here's a bigger receptive field, right? And so this one would be sensitive to edges at a different spatial scale than this one, right? So if you look at the zero crossing map that you get if you apply this one, you get these here. Okay, this is sort of, each line here corresponds to the zero crossing, okay? And this is for a medium level filter, and this is for the coarsest level filter. Okay. And interestingly enough, we have all levels, okay? We have, sorry about that. We have all levels, okay? So we have some ganglion cells which have this sort of receptive field structure, and others which are that. What is the use of that? Why do we have multiple levels like that? Because in terms of the correspondence problem, the next thing is, okay, think about this, okay, in terms of the output of the retina, you get this sort of picture, okay? And you have to make up what was the picture that you see, okay? Was it this? Was it something else, okay? So this is the output you get from one structure, from these sort of cells, and this is the structure you would get from another, okay? Now, what you have to do is basically, to figure out what the structure is to compare across levels, okay? So you want to compare this picture with that picture and with that picture. Why is that? Because if you have an edge, you would typically detect it in all spatial scales. So for instance, look at this here. So you see that this, whether you filter it through the higher frequencies or the lower frequencies, you still can see this sort of edge. Okay? So an edge you will see in all frequencies. We'll get back to that. I will repeat this in my next lesson where we're going to talk a bit about Fourier analysis. Okay, but basically, I want to sort of give the idea that, okay, it's useful to have a representation in multiple spatial scales. Okay, and we will see that this is sort of advantageous for specific reasons. Now I want to sort of, for specific reasons, not reasons. And I want to just conclude, because I have 5 more minutes, with one example, sort of perceptual example, which sort of can be understood using what I just taught you, and that's the Mach band. So Mach, Ernst Mach in 1860 found out, from simple psychophysics, that if you present something which looks like that, so for instance here, in terms of an intensity profile, this is sort of a bright area, and then there's a ramp here, and this is a dark area. Okay? But what you see, what you perceive is, of course, these bands. You see here a band which is light, this looks brighter than its surrounding. And similarly here, there's a darker band here. It looks darker. Although, if you were to measure this, as I said, with a sort of a photodetector, you'll find that this is sort of a ramp, and there's no edge here or edge here, which is brighter or darker, respectively. How do we understand this? Well, again, think about the convolution that I mentioned to you. Okay, so think about each of these retinal ganglion cells as having this. Let's think about now here on center cell. So they're like light in the center, dark in the periphery. So this one, would it respond very much? Tell me. This is a question. Not very much, right? Because, okay, has light in both the center and surround, and I said, okay, in that case, you don't get much firing from this one. Well, as you move, so we have an array here. As you move closer to this edge here, okay, so let's look at this cell. I mean, this basically what we're doing is sort of following the convolution again, right? So here, this cell, this would respond better than this one. Why? Because it has dark in some areas where it likes dark, okay? So this guy's response would be stronger than that one. How about this one? This one would respond weaker.
The signal is and what we see.
Hmm?
Can you repeat again what the actual signal is and what we see? I think
A sloped gradient.
Yeah, I'm sorry. Well, let me just explain. What you have here is an edge, okay? You have this bright part and a dark part. And now I'm trying to sort of understand, in terms of our perception, we see this as sort of looking something where the edge here is accentuated. And I'm trying to understand, why is the edge accentuated? And I'm trying to understand that in terms of the sort of filtering properties already at the level of the retina. Okay? And we said it accentuates contrast. So just to sort of lead the way, we'll try to show that, okay, these Mach bands can easily be explained by sort of the filtering properties already at the level of ganglion cells in the retina. And this is which is basically a convolution of the image with the filter, which is sort of center surround filter. Okay? And so now I'm looking at this and I'm saying, okay, how would a cell here respond? How would a cell which would be susceptible to this here respond, and so on and so forth. And we've seen that this cell here, which gets dark in its area, which is sort of in the surround, would respond better to this one, because here the center and surround are equated, so there's not much response here. Well, this one here would respond worse than this one. Why? Because it has dark in the center, where it prefers light, and light in the surround, where it prefers dark. Okay? So that would respond less than this one, and certainly less than this one. And as you move to this one, this would respond also pretty much at 0, because there's light and dark in the center and surround. So here's the profile that you could see. Here's A, B, and C, and D. There's a slight notice here that there's a portrait difference between A and D, and that's not what I told you, okay? But it's true that we are able also to perceive the fact that there's dark here and light here, although these cells are not sensitive to this. How do we do that? Any idea?
From what I understand, what you said earlier, we have the lateral and the lateral horizontal connection photoreceptors, so wouldn't the weakness in C, if they had a horizontal connection, may be the, let's say, the excitatory in B go up because that's how they're connected?
Wait. The lateral connections I talked about result in the receptive field properties I just mentioned, right? So they are, so if you have a center and surround inhibition, that surround area which is sort of prefers dark and center area which prefers light, that is because of the lateral connections which introduce this dark area, the surround effect, okay? Now, I said that, okay, we have here something which looks, I'll just summarize, we'll have to leave like in minus minutes, okay? So, I said that, okay, surprisingly, our perception is that this is a bright area and this is a dark area. But in terms of response, if the center and surround are equated, this should respond in a similar way than this one, right? Because here's a dark in both the center and the surround, and here's a light in both the center and surround. But there's an answer to that. Okay, how do you solve it? Right, the whole thing is we're talking about different scales. So if you have a receptive field which is this big, of course, then what do you get? You get the same thing, same structure, but it's more spread out, right? So this, if you have a receptive field which looks like this, okay, it would already sense the dark here, right? The problem here is this one, this receptive field does not sense what happens here. But if you have a bigger receptive field, it senses that, okay? So you have to think about this. This would be the, output of one type of cells with one spatial scale. But if you had a bigger neurons with bigger spatial scale, they would be more sensitive to this edge from further away. Okay? Okay, more to come in the next lecture. And if there's questions, I know it was dense. Okay, so if there's questions, please ask me in the next meeting, and we'll continue from there.
Can you upload the presentation to me?
Absolutely, yes, I'll do that. And by the way, if anyone here is interested in vision, we have another course that Svirot and myself are doing just now at 2 o'clock here on basic principles of vision and how can you infer them from functional imaging studies in humans. You are welcome to join. We just started, and this is the second lecture, so you've just missed the introductory one. So if you're interested, that's your chance.
זה יכול להיות אומן או אוף, זה תלוי מה מבחינת האינטרפרטטורית או האינדיבידואלית. עוד תכונה זה שיש לו סנטר סראונד, תכונה מסוימת ברקע, תכונה הפוכה בסראונד.
כן, יש לי שאלה
הפוכה בסראונד. יש פה כמה דברים אחרים, יש את או שהסנטר או הפוך בסראונד, וההפוך בסראונד. סראונד יש לך סנטר.
לוקח עכשיו, אני אסביר לך למה, אתה לוקח עכשיו פוטו, רספטור, ואתה שם אותו ליד האש.
זה תורם לאש.
זהו, זה מה שאמרתי לו לפני כן, והוא אמר שכמו ש-lateral inhibition מסביר, זה מה שאמרת לגבי
lateral inhibition חשוב גם לקונטרנט.
סבבה.
הוא מדבר עכשיו על התמונה, על כל האוכלוסייה. סקאלה אחרת של כל הוא מתצלם לי.
כן, התחלת איתו. יש כמה דברים שונים, יסודות כלא.
יסודות זרים, יסודות אחרים.
בעצם זה עוזר להוסיף את הדימויות בתמונה, של מה שאתה אמרת עליו, שהוא כל נושא, דיברנו על הדימויות כדי להשתיק כמה שיותר
אני חושב שזה עניין גם של יעילות של איזה אינפורמציה עוברת מתי, כי אם יש לך high resolution, כל הרספטורים היו מאוד מאוד קטנים, אז אתה מקבל רזולוציה יותר
בהתחלה הוא אמר על החייל לפני לא יודע כמה זמן אבולוציה, כן, אבל רואים את זה כבר היום.
הוא התחיל לדבר איתו,
הוא ראה שאין את זה לפני כן, אז הוא אומר שהנה פתאום יש חיה שיש לה את זה. לא יודע,
אתה דיקודר.
אתה רואה את זה שאתה הולך מההתחלה,
יש אינפורמציה
אז איפה האבולוציה?
מעט מאוד.
אם אתה מראה שאין את זה לפני כן, ופתאום יש את זה, אז יש אבולוציה.
אבל בעצם כל האינפורמציה נמצאת
יכול לקחת עכשיו חיה?
זה לא שינוי? אני לא יודע, אני לא ביולוגי.
הרזולוציה הכי גבוהה במערכת,
אבולוציה זה נכון? אם אתה רוצה להוכיח יש אבולוציה, ומה המקובל? מה בין אבולוציונרים לבין אבולוציה לא נוצרת ככה? מה זה נוצר ככה? אין כלום, יש צמח.
זה פשוט אינפורמציה שונה מאותה תמונה.
מה נוצר ככה? יש אבולוציה, זה אומר שיש חלקיקים הנחיות ביניהם.
אנחנו נוצאים הרבה פחות.
צמח מפותח, פטריה, שמר, חלקם. זאת אומרת שיש כסף. מי הכי מפותח שיש? תא בודד על האור שמרגיש אור. למשהו ביניים כזה, שמין חורים קטן מרגיש צבע, למשהו מפותח, שזה עין יכולה לשבת.
אז איך הוא קישר את זה ללאטרל inhibition?
לא קשור לך.
קישר את זה, הוא אמר, הנה, זה הקשר שלנו לחיה הזאת. הוא אמר, בוודאות, הוא אמר.
אז אני לא יודע, לא שמעתי. אני לא בכלל לא מבין שזה אותו פרקים. לאטרל זה הרבה פיזיולוגיה.
לא, הוא אמר, נכון, בכלל לא קישר את זה בהתחלה, הוא אמר, כאן זה לא נראה קשור. כאילו, הוא עוזר, ואז הוא נכנס לזה, אבל הקשר בין העין שלנו לעין הזה בעצם, זה שקיים לו, סליחה, כן, זה שיש כל העיניים הקטנות האלה, אז הוא אמר שיש, העין שלנו יש לנו קשר עם העין הזאת, וזה בא לידי ביטוי.
וגם,
וזה בא לידי ביטוי על ידי ה-lateral inhibition. טוב, זה משהו...
אין לי מושג. צריך לשאול את עצמם. אני לא רוצה עכשיו לפני.
סבבה.
כי לדעתי הלאטרל מסביר איך עובד עין בפנים, עין קטנות, ודמיון במינים זה משהו